Hello, this is a follow-up to the previous video, which was Introduction to Docker. Again, it's designed for primarily as training material for recently joined interns, but I think it will also be useful for anyone who's looking to know a little bit more about Docker and Kubernetes. This one covers it builds on what we learned previously about what Docker is and why it's important, and the kind of limitations of it and why we need container orchestrators like Kubernetes. Okay, so what did we learn in the last video about Docker? Docker makes deploying software easier firstly by encapsulating dependencies, whether those dependencies be application ones, system libraries, tools, or a configuration of the underlying Linux operating system. That helps with compatibility for if we want to run this application on different hosts. We know that it'll work because we've encapsulated all the variables that there may be between hosts. Also, it's made easier by saving network and storage costs due to its layered image format. This means that when you download multiple Docker images for different applications, the layered image format means that things that those two applications share can be downloaded only once, saving you storage costs and network bandwidth and associated costs. Docker leverages Linux container technology to provide some isolation between co-located applications. So if you're going to run two applications on the same host, they would normally be able to access, without other mitigating configuration, would normally be able to access each other's files and network traffic, but container technology gives us some isolation between these co-located applications. Also, we learned that containers are processes; they're not lightweight VMs. We saw in the previous video how we can see them listed along with other processes on the system using tools like PS and HTOP and the like. We also learned that the isolation afforded by C groups and namespaces, which are the two Linux technologies leveraged by Docker, that isolation afforded by C groups and namespaces is a trade-off compared to virtual machine isolation. And we make that trade-off because of the better resource utilization that we get as a result. In terms of amount of stuff we're able to run on the same amount of hardware, we kind of take that isolation hit for that efficiency. We also learned that Docker didn't invent Linux containers. The technology underlying them, C groups and namespaces, were committed into the Linux kernel initially by Google between like 2006 and 2010, around this kind of time. Not only by Google, of course. And but then when Docker came out in 2013, it's building on top of that, and it provides us a daemon that can run and supervise containers. Provides an image format, as we just described, for the efficient storage and transfer of applications. Also some network plumbing magic to wire containers together and give them IP addresses and allow them to talk to each other and that kind of thing. And it also provides some basic security features to restrict what containers can do. So even the most privileged containers, although very privileged and a very dangerous thing to run, can't do everything that a fully privileged regular process can do. Okay, so let's look at, we ran a couple of containers, or maybe one container, I don't remember, in the previous video, Nginx. But let's look at what an application would look like that has multiple components. So it's not just a single process, it's multiple components that talk to each other over network. You might call them microservices. So here's a sort of contrived example of one host, that's the blue box, running the Docker daemon, as we see there, the whale in the corner. And there are 5 components running an application that serves like static web content on port 8080. The port number is not important. I just want to show that some components will expose ports and some will not. Then the user will download those web pages in their browser and access them and interact with the site, which will make API calls up to the API on some other port on the same host, let's imagine. That API It's a front-end API which will talk to multiple back-end APIs. Let's say there's a customer API and a payments API, and so it's maybe some sort of shop, and they both talk to a database. All right, so I just want to give an example of how you'd put together a simple application with Docker, and explore some of the challenges we'll face when we want to progress from that. And that would be an interesting introduction to container orchestration. All right, so we have this simple app with 5 components. The web and API components about the public ports, the rest are not. So let's have a think about how, as developers working on these components, so say you're an application developer working on the API, let's say, how would we configure that API to talk to the other components? Remembering we're in a Docker world here. These are all running as Docker containers on one host. So often when you start up an application, you'll give it configuration, whether they could be command line arguments or environment variables or config files, to say here's the URL for the payments API, here's the URL for the customer API, that kind of thing. So how might we express that? So we learned in the previous video that Docker will give each container its own IP address. There was something in like the 172 range, I think. And so we could just configure the API with the IP addresses of the backend services. So we could say something like -- payments API equals http://172.0.0.2, and the other one is customer API equals 0.0.3. Let's just say we're making up these IP addresses. It doesn't matter what they actually are. We could use IP addresses and specify the ports and things like that. And that will work. However, what we will find is that if one of these containers, say the payments API, crashes and restarts, Docker as a sort of process supervisor will notice that process crashed and it would just start it up again. That's cool. It's like kind of like an init system would do. It's useful. However, when it does come back up again, it will likely, not always, but quite likely, have a different IP address. So what we have here is the problem we have is that we don't know these IP addresses for, say, the customer API and the payments API until they start, and then we can ask Docker for what their IP addresses are, which would mean we'd have to start these things in order. So start the database, get its IP address, configure the payments and customer API, give it the IP address. Then once they start up, get their IP addresses and give it to the API, and so on. It's doable, and as I say, if they restart, they'll get new IP addresses, which means we're going to have to reconfigure those components. All this will work, and if you're just debugging testing some stuff on your laptop as a developer, like it's fine. But it's an administrative burden. What we could do, just to brainstorm some ideas, we could maintain some sort of directory of backend services where that directory can be kept up to date with the current IP addresses of the services we need to talk to, and the API can always ask that for the addresses, and if it gets a connection failure, it will this just sounds messy, right? We don't want to have to. We'd like to just write our applications and assume there's a consistent address and a reliable network. Well, a reliable enough network at least to make a request that the name won't change, So if this sounds like a familiar problem, then you're right. This is generally what we use DNS for, right? So when we go to our browser and we type in google.com or .co.uk or whatever, that's ultimately going to resolve to an IP address, and it's actually going to go through quite a bit of infrastructure and forwarded from various places. But let's just simplify this and imagine that DNS gets translated into an IP address, which is the thing that we want to talk to, and we make a request there. All this happens under the hood in our networking libraries. This is the kind of behavior we want. This this problem of finding what our services are and identifying them by some name and then being able to make requests to them, this is called service discovery. And it is one of the problems that it's one of the features we've been missing in our example until now. Right, service discovery can be solved with DNS. So Docker helps us with this actually. It allows us to route by container name. So we could call the payments API container payments API, and then we will be able to make a request to http://payments API, then a port, I guess. And Docker has an inbuilt DNS service that the API container is configured to use as its resolver, so that it can make requests between containers by name. And as those containers stop and restart and get new IP addresses, Docker will update that DNS so that we, as users, don't have to worry about it. This is nice, right? So we have the process management supervision, where Docker will restart things when they crash, and we've got a consistent name to address them by, and we're good to go, right? We can configure all of these things at once before we deploy them, and know that the domain names will get resolved to IP addresses. We don't need to start them in order. It doesn't matter. It'll all just work. This is nice. But let's imagine we have a situation where, let's say, the payments API is slow. We find that it does some extraordinary amount of mathematical calculations. I can't imagine why, but let's imagine. And we want to deal with the bottleneck that has been caused by creating a second container of the payments API, or customer API, doesn't matter which. Let's go with customer API, because I believe the next slide is what requires me to have used that as an example. So we've got multiple instances of our customer API doing a strange amount of number crunching for a customer API, but never mind. So okay, we have a bottleneck there. We want to add another container of the customer API. Docker again helps us here because, let's gloss over the service discovery aspect of it for now. But let's say that when we add another customer API, we find this isn't going to work because one customer API alone is maxing out our CPU. So this host is too small to be able to support two big number crunching components. What we would need to do here is scale out onto another host. So we've gone to another host and we've put two customer APIs on there. Let's imagine that's enough because we don't have web API payments and database there. Now, apart from the service discovery and routing issue, which I'm going to gloss over at the moment because I don't want to get into Docker Swarm, but what we have now is two hosts with two Docker daemons in order to run all of our containers. Now, we need to be able to move to multiple hosts in order to be able to support a distributed application of anything more than the most basic application, because we need to be able to scale our components independently to deal with issues like this. In order for our application to perform and have the memory and CPU resources that it needs, we need to make scheduling decisions. Okay, we need to distribute customer API across hosts because of the CPU requirements. But we don't. And when we go to 3 customer APIs, we don't want to have to be forced to go to 3 payment APIs or 3 databases or 3 webs or 3 APIs. That's what I mean by scale them independently. But there's a problem here. These Docker daemons don't coordinate. They don't know about each other, at least not without further configuration. In our example here, we just spin up another host. We have Docker. We can't just assume that we can route to customer API and it would load balance across the multiple components, and B, that it will be able to route that traffic between hosts, in order for it to be able to do that, the Docker daemons would have to communicate and say, here are the containers that I'm running. These are also instances of customer API. You should say those daemons would have to say to each other, when you're load balancing for customer API, add these IP addresses too, which are on this host. That networking plumbing magic that Docker does is going to need to be extended to choose unique IP addresses across multiple hosts. They're going to have to coordinate on choosing IP addresses. They're going to have to be able to encapsulate packets, send them across a host, decapsulate them. If this is too much networking detail, it's fine. It's not important for you to know the details, but just recognize that simply by adding another host and running Docker containers on it, they're not automatically part of the same network. Our service discovery and network routing and DNS that Docker gives us is a single host thing. And so yeah, if we just do this naively, there's no routing between them, they won't have unique IP addresses. What we need is something to coordinate the networking across hosts, coordinate the scheduling, the IP address allocation. We need some centralized component to do this, and we call this an orchestrator. Okay, so what is a container orchestrator? It's I've used the emoji of a brain there because it's like it's a central component that makes decisions across the system. So it's an orchestrator, it's a control plane, it's various terms like that apply. So here we have a situation where we have three nodes, three hosts on which we are running containers. Some have more containers than others. We could also conceivably have another node that has no containers running but is still part of the system. And we have an orchestrator that makes central decisions in order to facilitate the kind of features we enjoyed in this simple scenario, but across hosts. Okay, and what kind of things will that orchestrator need to do? Firstly, it needs to know what's running where. So on this node, on the leftmost node, there are three containers, and they are what containers are they? What configuration do they have? What ports do they expose? What command line arguments? What Docker image are they running? All these things. It needs to know what's running on which host. It needs to know that information in order to update some internal DNS registry, so that when one service wants to talk to another by domain name, that name is backed by continuously updated IP addresses for the containers that will be serving traffic for those requests. The orchestrator, so we touched on networking there, the orchestrator needs to be able to route between containers across hosts and expose ports. One of these containers, if we're talking about the same application, one of them is the web and one of them is the API. So they will need to be bound on ports so that we can hit those nodes on certain ports and the traffic reaches the container. So some of that networking plumbing that Docker has been doing for us is another thing that a container orchestrator needs to manage. It needs to do some networking plumbing to allow containers to speak to each other. So if a container on one host wants to make a request to a container on another host, it should be able to make a request to the IP address of that pod, and some magical networking plumbing that the orchestrator configures will make that route possible, even though it's on another host. And we're using IP addresses of containers, not of hosts at this point, so we need some of that networking magic to do that. We also need load balancing and service discovery. So service discovery is the DNS that I was talking about that needs to be updated. We need to be able to route to services by name. And when we do so, we need those requests to be load balanced so that when we hit customer API, it doesn't always go to the same container if there are multiple. It will, for example, round robin between the various instances of the customer API. So service discovery and load balancing. We also need scheduling. So that when we say, I want to run 3 instances of the customer API, the orchestrator will need to make a decision about which host, on which host each of those containers should run. So we can imagine if we're going to launch 3 containers now with the system sort of laid out as it is now in the diagram. 2 containers are probably going to go in the rightmost node, and 1 container is probably going to go into the middle node. However, there might be more constraints on scheduling which we should be able to express, such as I need this container to go onto a host that has SSDs, fast disks, because it's going to do a lot of disk I/O, or one that has a volume mounted, or one that has a lot of memory because whatever operation it's performing needs a lot of memory, or it's say some video transcoding software that uses a lot of CPU and needs to go on a high CPU node. So configurable scheduling is another thing that an orchestrator needs to do. Also, logging and monitoring are considerations. It doesn't necessarily have to make opinionated decisions about which monitoring software to use or which logging software to use, but it needs to provide some way for these potentially short-lived and dynamically rescheduled containers for their logs to be gatherable somehow in a central manner. So that could mean tailing the logs of all running containers and keeping them centrally on the orchestrator, or sending them off to some other host, at least providing some way for you to reach them. You shouldn't have to SSH into a node and access the logs of a container in order to know what's happening with your services. You should be able to ask the orchestrator for some aspect of the system to get that information centrally. Likewise, monitoring, at the most basic level, as an operator, we need to know, are our containers running? Are they up? Are they healthy? Can we specify health checks that are custom for our application's needs? Are they under load? Do we need more? Do we need to perform scale operations? These kind of things. So, yes, container orchestrator needs to know what's running where. It needs to provide networking plumbing between containers across hosts and exposed ports. It needs to provide service discovery, load balancing, ability to make smart scheduling decisions that are configurable, provide some way to have centralized logging, and at least some basic monitoring. Now, I've worked up to this example from a single host just to kind of lead you along the path of the kind of challenges you'd face if you just use single host Docker. And note, I'm using generic language to talk about an orchestrators in general. Kubernetes is a container orchestration system. It does all the things that I've described, and it's one that we use, of course, at Influx, hence this video. It's not the only one, but it is the one that's kind of won the game, and it's the only one I'm going to really talk about in any depth. But in case those listening who know about Docker Swarm are wondering why I've omitted it, I've been talking about Docker in single host mode. You can also use a thing called Docker Swarm, which is an orchestrator, but that's not something we're going to discuss. We use Kubernetes, so I'll focus on that. Okay, so an container orchestration system needs to have all these features. Kubernetes is one such thing, and it needs to do these things at great scale. So it's important to remember that one of the drivers of container technologies is companies like Google running a huge number of applications at an unprecedented scale compared to what most of us would have been used to. So like mid to late 2000s, when these container features were being passed upstream into the Linux kernel, one might presume that before that Google were using them internally as a way to experiment with getting better resource utilization for their hardware compared to using VMs. The amount of applications that Google must run across their estate, not just for search, but Docs and Drive and YouTube and the myriad of chat applications, chat services that they have. They run a lot of software and they run it globally. And if they ran them all as one application per VM, that would be tremendously costly for them. I'm not privy to the cost and business decisions Google made internally, but it's a useful story to illustrate the journey towards containers. Once we reach a certain state, we make this isolation trade-off of VMs versus containers. Containers have less isolation than VMs. We make that trade-off because we need the scale that that containers provide. The amount of containers we can fit on a given host compared to the amount of VMs is much greater. They have a much faster startup time. They're not booting up a whole system, they're just like starting up a process. So it's important to remember that that's one of the drivers of container technology. So Kubernetes is a container orchestrator that is designed to handle this kind of scale, and indeed it grew out of Google's internal solution, which is called Borg, and it uses many of the same patterns that Borg uses. Not everyone has the infrastructure and scale challenges of Google. Very few do. So our reasons for adopting Kubernetes are not because we have those same scale challenges, but the way that it allows us to automate and orchestrate containers gives us a huge amount of benefit, even at a relatively small scale. If you only need one host, perhaps Kubernetes is overkill, but once you go to multiple hosts, the service discovery, load balancing, monitoring and logging features that Kubernetes gives us is worth the added complexity. And those scale challenges that Google have informed many of Kubernetes design decisions. Okay, so in the next video, I'm going to sort of complete the journey to Kubernetes from introduction to containers and Docker, and talk about how Kubernetes works in particular. So, thank you very much, and look forward to the next video.